All right, so let's kind of let's play around with this idea of null and alternative, and just kind of make sure we catch why things are good versus why things are not good. Okay, so here on the screen are 5 examples of some hypothesis statements. Some of them are valid and legitimate. Some of them have issues, and the ones that have issues, we're going to talk through what the problem is. So let's start with statement A. The null is the mu is 15, and the alternative is the mu is 15. Is that good or bad? That is in fact a terrible hypothesis. Well, the hypothesis part's fine. The alternative would be silly. It's what are you trying to prove? That it's the same as it started off with? No. So your alternative can't be equals. It needs to be some sort of greater than or less than thing. Statement B. Okay, x bar is equal to 123, and alternative is that it's less than 123, and that actually is not cool either. The problem being the variable that they used needs to represent the population and not the statistic, not the sample. Okay, so x bar is the problem in that case. Statement C, pi equals 0.1 versus pi equals does not equal 0.1. That actually is a good one. The pi symbol is representing for a population proportion, so that one we're fine. And it's a two-tailed test, so it's not equal to. We can have a not equal to in there, just can't be equal for the alternative. All right, statement D, p equals 0.4, and the alternative is p is greater than 0.6. Is that good or bad? And that one's bad. The problem is the numbers need to match. It needs to, if we're going to, the null being 0.4, we need to gather evidence against the 0.4, not some other random number that we picked. And then the last statement is p hat is equal to 0.1 and p hat is less than 0.1. And that problem is the variable again. The variable needs to be some sort of parameter and not a statistic, and p hat represents a sample proportion. Okay, so let's talk about p-value for a second. P-value is used when we assume the null is true, and it is the probabilities that a given statistic, so the sample, has a likelihood of showing up as extreme or more extreme than what we actually observed. In other words, when I'm looking at the data, is the observation that I have, is the sample that I have something that is very common, sort of middle of the data percent, or is it something that's rare and shows up in the tails of the data? Okay. All right. Level of significance is how we determine whether or not we think there's evidence for or against a particular claim. So we define level of significance to be the amount of evidence necessary before we begin to doubt that the null is true. It is the probability that we will reject the null assuming that it is true, and it is given by this alpha, which we've seen in error, representing type 1 error. Well, it's the same number that we will also use to represent the amount of evidence that we will reject or fail to reject a claim. In reality, alpha can actually be anything. The 3 most common values are 10% or 0.1, 5% or 0.05, or 1% or 0.01. And the most common is 0.05. So if in the problem it doesn't state a alpha level, then we just go with 0.05. But it is okay to pick other values. And if you recall, when we talked about error before, the consequences of type 1 and type 2 error dictate which alpha level we actually would ideally go with in a given data set. But again, it's not set in stone that it has to be a particular value. It's just typically, out of fairness, you probably want to decide what your alpha is going to be before you actually go out and collect the data. Okay, so what does it mean if something is statistically significant? That actually is a phrase we associate with a p-value, and the numerical way we look at it is if the calculated p-value is as small or smaller than the level of significance, then we can claim something is statistically significant. Okay, So sort of break it down in a mathematical formula. If the p-value is greater than alpha, in other words, if the probability of a given sample is bigger than what the alpha is that level we get excited about. So if the sample p-value is larger than what I said I'll get excited about, then I'm not excited. We claim that we failed to reject the null at that given level. If the p-value is in fact less than alpha, then we reject the null at that given level. Okay, so again, the p-value dictates whether we reject or fail to reject the null, based on whatever the null level is. Okay, so about that p-value, we use the p-value to make decisions about the null statement. Large p-values show support for the null, but never that it is true. In statistics, we are not saying something is true. We are suggesting that there's evidence for or against something. Small p-values show support that the null is not true. Again, we're not saying something is false. We're not saying we have proven. We're saying that we've got evidence for or against a particular claim. And then for a two-tailed test, we simply double what we would for a one-tailed test, is how the calculator does that. And lastly, and this is just verbiage, we never accept the null. No matter what the data tells us, no matter what the p-value tells us, it is not evidence that it is true. It's kind of like a murder trial. Just because they didn't find evidence of guilt, that doesn't mean we assume innocent. We just say we just found him not guilty. Doesn't mean the guy didn't do it, we just couldn't prove it. Same thing with the null hypothesis. We never accept the null. Now I'm going to emphasize this a couple more times just to get the point across. So never accept the null. In other words, don't ever say I accepted the null. Never accept the null. And one more time just to hit it home, never accept the null. Alright, so let's go through some practice statements and see if we got the big idea here. At an alpha of 0.05, would we reject or fail to reject the following null statements based on the given p-values? So if I got a p-value of 0.03, would I reject or fail to reject? 0.03 is less than 0.05, so we reject it. There is evidence against the null. 0.15 is larger than 0.05, so we failed to reject. 0.45 is larger, so we fail to reject. And 0.023 is smaller, so we reject. Okay. Alright, so how do we get to calculating these p-values? Well, for a z-test statistic, so for a z-score, or in this case our proportional data, we're going to use a normal CDF. And in the normal CDF, it's going to calculate a lower bound and an upper bound. And that's going to be given on the parameters of the problem, so we'll kind of look at some numbers we can type in. Now we're going back to looking at z-scores from a standard normal curve. In other words, we're calculating a z-score based on the proportional data, just like observed minus expected divided by standard deviation. This time standard deviation of the given sample. And we're again going with the idea that these are standard normal curves here. So when we look at the norm CDF in a moment in the calculator, that's the given parameters of that normal CDF is that at 0 and 1. For 0 for mean, standard deviation of 1. And again, that's something your calculator automatically does, so you don't have to really stress too much about that. Okay, so let's actually play with our calculator for a second, and let's look at drawing and shading curves and p-values. Okay, so we're going to turn our calculator on, and we're going to go to the distributions menu. So on my calculator, it's right above the vars. So hit second, vars, which pulls up the different distributions. And we're going to go to norm CDF, which is choice 2. And in norm CDF, it's going to ask for a lower bound and an upper bound. Now, if your calculator doesn't have this feature, you can just type in the numbers for lower, upper, and it'll also give you the same number that I will have. Okay, so let's kind of think about a right-tailed test. I am got a z-score, and I want the very rightmost of this particular value. So let me kind of get a picture going here so we can kind of see graphically what that looks like. And so that's what I'm trying to type in the calculator. Now this bar right here, they've actually calculated the z-score for us. This bar would be 1.6. So I want 1.6 at the bottom end, and I want everything up above it. So the lower is going to be 1.6, and then kind of clear that out, and I'll kind of explain this. Now this curve, this tail actually goes on forever. So I want a number that represents forever. Mathematically, we would say infinity, and some very nice modeled calculators actually will let you type in infinity. You might not be able to. So the way we get around that is we go 1 e to the 99 power. So this is scientific notation for 10 times, 1 times 10 to the 99th power, which is 1 with 99 zeros after it. So it's a really big number. So to get 1e to the 99, you're looking for what looks like a double E somewhere on your calculator. And I'm going to hit second, whatever button's associated with it, and then just 99 after that. Now, because we're dealing with the standard normal curve, you'll have a 0 and a 1 in there, and most calculator models will have default to that. So in other distributions, you can actually change that if need be, but for right now, that's fine. 0, 1. And let me kind of show, for those that don't have this fancy calculator at home, you can actually just type this in. So normal CDF 1.6 comma 1e to the 99 comma 0 comma 1, and then it should give you the same number as me. And that number is 0.0547. So I would expect this particular data, however they got the sample, I would expect that to show up 5.47% of the time. A little bit larger than a common alpha. Okay. That brings us to the other question, the two-tailed test with a z of negative 2.4. So let me kind of get a picture of that going here. So that's what we're trying to calculate, is that probability. Now that negative 2.4, you have to kind of think, where is that in a normal curve? Well, if here's the mean of 0, negative 2.4 actually puts us on this bottom end. Okay, and that's fine that it does that. But that means this is 2.4 and this is 2.4. Just that border where that darkened shaded area begins. So I want a probability. I'm going to figure out the lower end probability, and then I'm going to just double it to get the upper end, and that'll be the not equal to probability. So I'm going to go right back to distributions, norm CDF again. This time, since I'm doing the lower part, that's going to be negative infinity, so that's negative 1e to the 99. That's what negative infinity would look like on this particular calculator. And then I want the upper bound, so this line right here, I want that to be negative 2.4. And then I'm going to hit enter. And I'll kind of pause there so those that don't have this fancy calculator can kind of type it in and get caught up. So there's a lower bound, there's the upper bound, the mean, and the standard deviation. And then when I hit enter, I get 0.008. Okay, but that number only represents the lower bound. I want both tails. And so that 0.008 was the bottom end, so I have another one for the top end. So I just want to take that number and times it by 2. And a lot of calculators will let you just hit the multiply 2 button, and it'll actually give you a p-value of, in this case, 0.01639. Okay, so there you go, in case you missed any of those statements about the p-values.